Okay, so now we're going to do something at least half useful using OpenCL, and it's something called numerical reduction, which just adds all the elements of a collection and then produces a sum at the end. But we will come across some new areas of OpenCL, such as using local memory and memory barriers. So, our device can have a certain number of work groups, and it can have a certain number of work items in a work group. And so this demonstrates the local memory of one of my many work groups. So I can have up to the maximum work item size defined by my device. So on my CPU it's 1024, and on my graphics card it's 256. So, but for this example, I'm just going to pretend that I've only got 8 work items in a work group, just so that I can demonstrate this numerical reduction easier. So, we're going to loop over all of these, but only over the first half, but we're going to incorporate the addition of the other half into it. So what I'm going to do, I'm going to start at the first element, and then going to add the sort of the mirrored element over the halfway line. So I'm going to add 1 and 5, so I'll get 6. I'm then going to add 2 and 6 to get 8. I'm going to add 3 and 7 to get 10, and then I'm going to add 4 and 8 to get 12. So that's that iteration done. So I've summarized 8 elements into 4. I'm then going to repeat this process. I'm going to add 6 and 10 to get 16, and then 8 and 12 to get 20. And then repeat it once more so that I'm only left with 1 element. So I'm going to add 16 and 20 to get 36. So this 36 is the sum of these 8 elements. And it's going to be stored at the ID of the first work item in a work group. And so it's going to do this for as many work groups as possible that occupy the array that I started with. So if I had an array of 16 elements, then it's going to do this twice, and I'll be left with 2 items left. So one here, and then if you imagine this whole thing over this side, then I'll have another one here. I'll store that into a global out buffer, and then I can add those together to produce the final result. So let's get cracking. Oh, and also a disclaimer, the first time I tried to record this, my PC crashed, and that's because I introduced a infinite loop in my kernel, and apparently my graphics card doesn't like that because it freezes my entire PC. So I had to shut down and record this all over again. So the first thing I'm going to do, oops, I've already got it open, is change this to CPU, because my CPU doesn't crash basically when I fuck up quite badly. So it might be a good idea for you guys to do that as well, because I don't want your PCs to be crashing. And then once you've got your kernels working as well as you can, bug free, not crashing, then you can change it to GPU and it should work fine again. Okay, so for now I'm going to keep it as CPU because I don't want to have a risk of it crashing again. So I'm going to create a new project, Numerical Reduction. Same thing we've been doing over and over again, create an empty project. I'm going to create a 64-bit version of this project. And click build on that. Then going to do something I always forget to do, which is add a reference to my helper project, which contains that create program function that I've been using. Then need to add the property sheet, which contains the linking options and include header directories. so that I can actually use OpenCL. I'm going to create a main file for it. Call it the same as the project, Numerical Reduction. I'm going to, oh, it was already highlighted from previously. I'm going to copy this across. I'm also going to set this as the starter project. Okay, so let's get our collection. I'm going to use a vector of 1024 because I know that my maximum workgroup size is not greater than this. I'm then going to iterate over each element. I know my compiler will complain because you can't use an index of an int into a vector without it warning you because it's not the same size, but I don't care because I've only got 1024 elements. And what am I doing? Yeah, so I'm going to store the index into the array at that index, into the vector at that index. So my vector is just going to contain 0, 1, 2, 3, 4, blah blah, all the way up to 1023. I'm going to create my buffer. Just going to contain this. So some context. I always use the sixth constructor. So I want my device to be able to read this. Then read it. Come on. I didn't find it. CLMM read only. I want my host to not be able to do anything. So host no access. And I need to tell it how to transfer the memory across because I am giving it some data. So I'm just going to use CLM host copy host putter. I need to know the size. That's just the size of the vector, and I need to pass a pointer to the vector. I then need to create an output buffer to contain the results from each work group. But I need to know the size of the workgroup first, so I actually need to do this in a bit of a reverse order. CL kernel program, and then the name of the kernel, which is going to be Numerical Reduction. I need to change the file name, the OpenCL file to match. And then I'm going to call a get workgroup info on the kernel. So CL kernel workgroup size. So I want to know the maximum amount of work items I can have in a workgroup. So then I want to know the number of work items in my workgroup. It's going to be the size of the vector divided by the workgroup size. Oh, this hasn't resolved because it needs to know the device. So I want my output buffer to be able to be written to by the device. Right only. I want to be able to read it, so I want host read only, and I'm not going to be passing it into the device, so I don't need the third flag. I do need to know the size, which is just num_work items, and I don't need the other argument because I'm not passing in anything. But I think before I continue, it's probably easier if I show you what the kernel's going to be doing. So create a new one. Kernel void and then numerical reduction. So it's going to have some global data. For the first time, we're going to use some local data. Just call that local data. I can't think of a better name. And then we're going to have some out data. So this is going to be the entire vector. this is going to be the number of, well, it's going to have the same number of elements as the maximum work group allows, and this is going to be basically this divided by this, the number of elements. So we want to know the global ID. Just get global IDs here. I want to know the size of the work group. So get local size. So we're only in one dimension, so it's all going to be zeros. I want to know the local ID. So remember, the local ID is the ID of the work item in a work group, where the global ID is the work item among every, is the ID among every work item being executed across all work groups. So we're going to want to do a for loop. Ideally, you should keep for loops as minimal as possible inside a kernel. So let's say I, and this is going to be equal to the local size divided by 2. And if you remember from previously, I'll just drag this across. So we're going to start the first iteration with 4 elements. So get local size will be 8. Well, for our simple example, it's 8. And so the first iteration is going to be 4. And so inside, I want to be able to add the corresponding elements. But before I do this, I need to transfer the memory from global memory into the local memory. So I need to get the ID locally, and I'm just going to make that equal to the global memory. But I can't start oops, what have I just done? See, I have a habit of pressing Control S every 10 seconds because I have a fear of my computer crashing or breaking down, and I haven't saved it, so I'll save it, so otherwise this is going to keep popping up. So let's do that to steal the name. Cool. Yeah, so going back to this example, so I'm going to have 4 work items which need to access the data. However, if my first work group, my first work item has finished executing this, it's going to start going to the next iteration. However, these elements may not have been populated yet if the other work items haven't executed. So this, then it's going, on the next iteration, it's going to read in garbage. So what I need to do is have a memory fence or barrier to force everything up to this point in all the work items in my work group to have finished executing. And that's CLK local mem fence. So you can have local mem fence and global mem fence. If you're just dealing with synchronizing read and writes to local data, then you use local mem fence. If you're synchronizing to global data, then you'd use a global mem fence. Okay, and then I'm going to want to divide this again by 2. I made an equal there to make sure it's written back to I. So what we want to do now is check that we are in the lower portion, in the lower half, because this loop's going to be executing for all these elements, but we want to make sure that we're only processing the first 4 and ignoring the others. So I is going to start off at 4, so I want to make sure that my local ID is less than that, and then I'm going to add the local ID plus equal the element. Let's bring it back up. The element over here, so it's going to be the local ID plus the current local size divided by 2, which has already been accounted for here. So that's just local ID plus I. And I'm also going to want another barrier here to make sure it's all synchronized properly before it goes on to the next iteration, like I described earlier. So then once that's done, I'll be down here. So I need to check, am I the first work item in this work group? If so, save that out. So I'm going to check if the local ID is the beginning. If so, I'm going to call get group. Notice group, not global, group ID, which gets me the ID of the work group in all the executing work groups. Because so in this case, this is much smaller compared to this. So I can't use get global ID because it will reference the, it will just overflow entirely. So this is the one I want to use. And that's going to be equal to local data 0. I think that's all I need to do. So yeah, so the reason I got a crash before was because I had put local size here instead. So I was never decrementing. So I was always greater than 0. So this loop was just infinitely running. Okay. So I've already created my kernel. Let's set the arguments on it. So this is the main buffer. So the next one, if you remember, is our local buffer. You don't create a buffer object on the host side for this because it can only access global memory. So you have to just allocate enough memory for it. So we know it's going to be int times the work group size, because I'm shoving the maximum number of work items in there as possible. And always make sure to put null putter at the end, else this will resolve to the same as this because it's just passing in a pointer. So always make sure you've got null putter at the end. And then the last one's going to be my output buffer. Should really be numwork groups. Don't want to make it more confusing than it already is. So I'm going to create a queue. My context and device. Going to do what we've always been doing. So I pass in the kernel. There's no offset. So the global size is going to be the vector size, and we need to pass in the local size, so how many work items in our work group, which is just going to be work group size. And so this always has to be a multiple of this. So I have chosen 1024 like on purpose. It wasn't just a random number I picked out. It had to be a multiple of this size, and I know that both my devices are that. But in another video I'll show you how you can just have any arbitrary number there. So I want to be able to read this back in. So this is the out buffer I'm reading in. I want it to block. no offset. The size is the output buffer size, and I need to make a vector to store that. So it's out vec, and that's going to be this numwork groups. So it's going to be size of int multiplied by out vec size, and then pass in the pointer to the vector, and then just do the usual so that my command prompt stays open. Okay, let's try execute this. So size 0. Numwork groups is 0. What is that? Work group size is a trillion bazillion. Wow, something's gone wrong there. Why is that then? Okay. Let's start debugging then. So this takes an error argument. Minus 48. Invalid kernel. It doesn't like our kernel for some reason. Oh, I've got, first of all, I've got 2 brackets there. That probably doesn't help. Let's try that again. Okay, cool, let's fix that. Okay, I've now got 1, which is correct because my work group size is 124. So I've got 1024 work items in a work group, which is the exact same as this, so I'm only going to have 1 work group. And that should contain the sum of them all, which it doesn't, 0. Okay. Okay. That was because I wasn't passing in the size of the bytes. I was just passing in the number of elements into both the buffers. So, let's give that a try. Oh, we've got a number now. It looks reasonable enough, maybe, I don't know. But we can find out by summing all of them up in the original for loop. So here we get 523776. 523776. Cool. So you're probably thinking, why the fuck didn't you just do this from the beginning, you idiot? Well, you're partly right. It's because you wouldn't have learned all these awesome other features of OpenCL, like local memory and fences, which are all very important topics, and this is probably the easiest example you could do to demonstrate it. But of course this has only got 1 element. Ones if we had a couple in there. So I'll just double the size of this, but now we're left with 2 elements. 2 elements which are not summed up correctly like this one is. So the easiest way to solve that is to use the std accumulate algorithm, sorry. Could just use another for loop, but you know, we like to be more modern here. So I'm going to pass in the start and end iterators. They can be constant because they're not being modified. What's the begin end? We'll start at 0. So this will be the sum. Yeah, it's the same. Sorry, I did that a bit quick. It's the same. But now we're doing work on the CPU side again. And if this was a really large number, we may end up having to iterate over quite a few of these. If our workgroup's size is very small. So I'm not going to discuss it in this video because I think I've badgered on for too long already. But what you would do is create yet another kernel which would execute once you've gone past the threshold of the maximum work group size. And then on your last one, after you've finished executing this, you would then execute another one to add all those together in a similar fashion using reduction again. And then you can get an even further speed increase, whereas instead of using ints, you use int 4, so you pass in 4 at a time. It's actually quite a bit faster. So that is yet another thing you can do. But I will leave that with you for now.